Welcome back to our podcast, where we delve into the intriguing realm of databases and transactions. Today, we're focusing on a crucial aspect of database management, transaction isolation levels. We'll unpack how transactions operate, the challenges they encounter, and the methods used to uphold data integrity. So, get comfortable and let's dive in. One of the primary challenges in database management is concurrency. When multiple transactions occur at the same time, they can interfere with each other, leading to inconsistencies in the data. Imagine two transactions trying to update the same room booking simultaneously. In such cases, one transaction might have to wait for the other to finish, thanks to locking mechanisms that help prevent conflicts. This is where locks come into play, particularly shared locks and exclusive locks, which ensure that transactions don't clash. Locks function like traffic signals at a busy intersection. Shared locks allow multiple transactions to read data but prevent any from writing until the lock is released. Exclusive locks, on the other hand, grant one transaction complete control over a data item, blocking others from accessing it until that transaction is complete. This system helps protect against anomalies like phantoms and write skew, ensuring that transactions are executed in a serializable manner. When it comes to managing concurrency, there are two primary strategies: pessimistic and optimistic concurrency control. Pessimistic control assumes that conflicts are likely, so it locks resources to prevent them. While this can lead to longer wait times, it ensures safety. Optimistic concurrency control, however, allows transactions to proceed without locking resources at first, operating under the assumption that conflicts are rare. If a conflict does occur upon committing, the transaction is aborted and must be retried. Now, let's explore a more advanced concept, serializable snapshot isolation, or SSI. This approach combines the benefits of snapshot isolation with mechanisms to detect serialization conflicts. Under SSI, transactions operate on a consistent snapshot of the database, meaning they don't see uncommitted changes from other transactions. This isolation level helps prevent anomalies while allowing for greater concurrency. One challenge that arises with snapshot isolation is a phenomenon known as write skew. This happens when a transaction reads data and then writes based on that data, but by the time it commits, the data may have changed. For example, if a transaction reads that two doctors are on call and then assigns a patient to one of them, it might be acting on outdated information if another transaction has modified the on-call status in the meantime. To tackle these issues, databases often employ multi-version concurrency control, or MVCC. This technique allows transactions to read from a snapshot of the data at a specific moment, ignoring any changes made by other transactions that haven't yet committed. This approach helps maintain consistency and reduces the likelihood of conflicts. In the context of SSI, while transactions read data, the database keeps track of which transactions have accessed that data. If a transaction tries to commit and finds that another transaction has modified data it read, it must abort. This ensures that no transaction operates on stale data, preserving the integrity of the database. However, tracking reads and writes does come with its trade-offs. More detailed tracking can enhance accuracy in detecting conflicts, but may also increase overhead. Striking a balance between precision and performance is essential for efficient database operation. One significant advantage of SSI is that it allows transactions to read data without blocking other transactions. This means that read-heavy workloads can function more smoothly, as read-only queries can run on consistent snapshots without waiting for locks. This design principle significantly boosts overall database performance. A key takeaway from our discussion is that transactions are designed to simplify error handling. Instead of grappling with various concurrency issues and potential faults, applications can simply abort and retry transactions. This abstraction allows developers to concentrate on higher-level logic without getting bogged down by the complexities of data consistency. As we wrap up today's episode, it's clear that transaction isolation levels are vital for maintaining data integrity in databases. From understanding the nuances of locking mechanisms to exploring optimistic concurrency control and the advantages of SSI, we've covered a lot of ground. Remember, while simple access patterns might not require complex transaction management, as your database interactions become more intricate, leveraging these transaction strategies can significantly reduce errors and enhance performance. Thanks for tuning in, and we hope you'll join us next time as we continue to explore the fascinating world of databases.